Hello, welcome back. In this segment, I wanted to discuss what happens if you compare, say, an unsigned short type with an unsigned integer type. These are two different sizes, right? For the unsigned short integer, usually it's 2 bytes. For the unsigned integer, 4 bytes. So you're comparing a 2 byte data with a 4 byte data. So what will happen? Is it like, will it drop the 4 byte data and compare the 2 bytes, or it will do some extension on the 2 bytes to make it to 4 byte scenario? Okay, let's consider this particular example where we have I is one's complement of 0. That means essentially all of these bits of I will be 1. Okay, that means it's 2 power 16 minus 1, right? That is the meaning of I. So in binary, it will be 1, 1, 1, all the way until the end 1 16 times, because unsigned sort is 16 bits. What about unsigned integer j equal to 1's complement of 0? It will also be a bunch of ones, but this time it will be a lot of ones, 32 ones. Okay, something like this. Now we are asking, are these two numbers not equal? Okay, so I wanted to spend some time, look at the assembly code and understand how the compiler actually generates code for this. Okay, let's do that. By the way, the answer is this is going to be 1, meaning I and j are not equal. We can look into the assembly code and understand why they are not equal. Okay, does the compiler looks at the length, or does it look at the small data in terms of the size and put some zeros in the front, right? And then compares these two things and then concluded that, okay, they are not equal. Let's look at the assembly code for this little toy example. Okay, how do we do that? We can compile and load it into GDB and study whether I not equal to j is returning 1 inside GDB, for example. So I've already compiled this code, and if I run it, the status is 1. Okay, it means the program is returning 1 to the caller. Okay, that means I and j are not equal. Now let's load it to GDB and study this. Okay, I already compiled and loaded it into GDB, and we can quickly go through this code and understand what's happening here. Since we already saw the C code, it should be easy to map the C code into assembly code. Remember, my I was just a short integer. So in terms of assembly, it will be move W. Okay, so W means word, and FF in hex means bunch of ones, 16 ones, right? So this must be I. So this is I, our I. Okay, and this must be our J, because you can see it's move L. It's 32 bits of 1, so this is our J. Okay. All right. Don't worry about other statements. I'm skipping some statements just to get the core idea across. We talked about move Z earlier in other segments. Move Z means put a 0 extension in the front for a word, okay, and make it too long. So this is, you can imagine this is like casting. Cast the variable I from short integer type to an unsigned integer type. Okay, the L means 4 bytes, right? So move ZW takes the data that is stored at EBB minus 6, which is nothing but I, and puts zeros in the front. That is the meaning of the Z. So essentially, what's going to be stored in EAX register is like this: 2 zeros in the front, 2 zeros of bytes. Okay, meaning this is 2 bytes of zeros, and then your 2 bytes of FF. Okay, the totally 4 bytes. Okay, so this is basically what is being stored in EAX. What about this comparison statement, which is going to compare whatever you have in EAX with EBB minus 4, which is nothing but J. And of course, comparison will fail because what is there in EBB minus 4 is FF, and the rest are also 2 more bytes of FF. Okay. And the comparison is going to fail. These are not equal. So when there is a not equal, the AL flag will be turned on. Okay. So what will happen at this point is that the EAX register will have 0, okay, 0, 0, FF, and then a 0, 1. Okay. And what are we doing now? Next statement, we are taking AL. AL means just the lower part of EAX, which is this part, 0, 1, and move it to EAX register. But we are doing a 0 byte extension, meaning all of these 3 remaining bytes will become 0. So essentially, EAX will have 0, let me write it here, 0, 0, 0, 0, 0, 0, 0, 1. Okay, that's all. We can confirm by compiling and debugging it like this. Let's do that. Let's put a breakpoint, right, at this location and run it. Okay. Okay, let's see what is there in the EAX now. EAX should have only 0, 0, 0, 0, FF because of this statement, right? So let's look at that. Print /x $EAX. Yeah. Of course, the 0 zeros in the front are not shown. Okay, so you can see it's FF. Right. But you can then perform the set not equal operation, right? The comparison actually failed. So we should be able to, we can actually even print the E flags. It's not important if you don't know E flags at the moment. Don't worry about it. We don't need to worry about E flags. Let's focus on the next step. The comparison operator finished its comparison, and the answer is not equal to 0. Otherwise, you would have seen a 0 flag set. Here, there's no 0 flag set. So what will happen now to the EAX register? The EAX register will end with 0, 1, as I said earlier, because of the set not equal to operation, setting the least significant bit of EAX to 1. And next statement says 0 out the EAX except the least significant bit. Okay, so AL has already 0, 1. Now, if you look at the next statement, yep, everything else is zeroed out, only 1 is remaining. That's basically it. So if you have a short type and you're comparing it with a long type, the compiler will actually do a 0-bit extension for unsigned numbers. For signed numbers, of course, it will do a signed bit extension, which we talked earlier, and then it will compare. Okay, that's the reason why the numbers are not equal in this comparison.